Welcome everyone. We are now discussing different architectural changes that we can do to MLP to cater to several different topologies of data. We looked at one such architecture which we call the convolutional neural networks in the last class. So in this version we will look at another class of architectures that are called recurrent neural networks or RNNs. So these kinds of neural networks are typically applied to data that has a sequential topology. So what is a sequence? So sequence is a set of observations that has one more temporal observation. There is no strict definition of what a sequence is, because one can, okay, this is one other important point that I want to make. See, one can rearrange the data, which are tensors for our case, into any topology and use any architecture. So what I mean to say is that suppose you have a sequence, okay, you can arrange that as an image and use CNNs for it. And suppose you have an image, right, you can arrange that as a sequence and use recurrent architectures for it. That's exactly what is done in something called VIT, visual transformer, which we will see later. So this is an important point, that you can rearrange your data into whatever topology that you would want and use any architecture, okay. But typically you assume that your data has a certain type of topology and use that particular kind of architecture. So today most of the machine learning tasks are solved using this architecture called transformer. So transformers are originally designed for a sequential data topology, but now they can be applied for image kind of topology as well, which we will see in the later parts of the course. But the point that I wanted to make is, it's not strict that okay, if you have a sequence you will have to use a recurrent neural network, and if you have an image you have to use a CNN or anything. So any kind of architecture can be used on any data as long as you can view your data, or rather rearrange your data that suits that particular architecture. So that's the point. Okay, so recurrent neural networks, so suited for sequential data topology. Now a sequence data, let's consider one particular data point. So let's do everything for one data point. Consider a data point to be of following nature. So we have x to be equal to, so this now x is a sequence so x to x capital T, where xt is a d-dimensional vector. So this is a single data point. Understand? So what we have is a sequence of vectors, a T length, capital T length sequence of vectors. Each of the element of this sequence is a d-dimensional vector. You see what I am saying? Okay. So examples for this can be natural language, and it can be a clinical time series, it can be a video or anything, right. So how is a natural language a sequence like this? You have a sentence is a collection of capital T number of words, okay. So each word can be represented as a d-dimensional vector using one hot representation in the dictionary. That's one of the representations. So you have every sentence is a d-dimensional, is a T length sequence, okay. How do you look at clinical time series this way? Suppose you are making measurements, okay, and you make 5-6 clinical measurements at every time, and you make 100 measurements over time. That becomes one data point. So please note that we are talking about one data points, and our data set will have several of such time series. That would be your data set. Does it make sense? And how is a video a sequence? Is that every point is now an image, a d-dimensional image, and we know how to see an image as a d-dimensional vector, and that becomes a sequence. Got it? Right. So now labels for this, or rather if you want to solve supervised task for this, a supervised task on this can be of multiple types. Okay. So let me write that down. Example tasks on this data. One is now sequence classification. So sequence classification is an example where given a time series you assign a scalar label to it. Example of this can be let us say emotion extraction from text. So given a paragraph, you tell me whether this paragraph denotes a happy expression or a sad expression or something, right. So this is a K class classification problem, and the data that you have are sequences. Does it make sense? Right. So this is one way to look at one possible task. The other more prevalent kind of task that is considered is sequence to sequence regressions. These are also called seek to seek tasks, okay, sequence to sequence regression tasks. What is an example for this? The classical example is translation, also called as machine translation. Where the input is a sequence and the labels or outputs are also sequence. Do you see the point? Right. So or you take video generation, right, or you have a video as an input or a text as an input, and you need to generate a corresponding video, a video corresponding to it. So let's say you have a sequence as an input and or a text, text as an input, and you get a sequence, another sequence as an output, and so on. By the way, another point is that one can use these architectures as Lego blocks, okay, and place one after the other for tasks as one seems fit. You already saw an example, right? You know, whenever we solve a classification task using a CNN, you have several convolutional layers followed by an MLP, which is also called a fully connected layer. So similarly, one can have a recurrent architecture followed by a convolutional neural network as well. So an example can be, let us say that you need to solve this task called image description, meaning you are given an image as an input and the output has to be natural language description of what is there in the image. Now input will be convolutional layers, so an image is given as an input to the convolutional layers, okay. Generate a vector, on that vector take that as an input and have a recurrent architecture as the output, where the recurrent architecture gives a sequence as an output. Now that sequence is your output. The only thing is, depending upon what your task is, your data has to be in that format. Meaning, suppose you are solving this task that I just talked about, which is image description, then your data has to be an image and the corresponding description. That's when you can define a loss function and solve ERM on top of it. Please remember that irrespective of the architecture, okay, irrespective of the task that you are solving, ERM still stays the same. It is the same ERM, same gradient descent that we will use to solve the problem. Fundamentally, whatever we saw in the first half of the course is still remaining, right. So there is still bias variance decomposition and so on. What changes is the kind of task that you solve. Does it make sense? Yeah. So these are some examples of how to do it. So one issue with sequences is that every data point that we get may be of different length. So let us write that. In sequential data, every data point may be of different length. if you look at an example, suppose you are solving the translation task, let's say English to Hindi or something. Every input sentence has a different length. Capital T is different. Okay. So now one needs to handle that. MLP cannot handle this, isn't it? Because an MLP or a fully connected neural network assumes that every input data point has the same dimensionality. Please note that I am not talking about this RD here, I am talking about this capital T. Capital T can be different for different input points, the length of the sequence can be different. So the architecture has to handle this kind of a thing, right. So to do that, different length, and therefore this MLP cannot handle them. Unless you zero pad all of them to have same length, that can be done, but that's not the most elegant way of doing it. The other part is, if you just treat all of these, concatenate all of them and make it into a D cross T long vector and give it to an MLP, then the sequentiality of the data will be lost, because for an MLP it does not matter if you show that, I mean if you swap the data dimensions, or rather if you shuffle the input data dimensions, MLP will still do the same thing, because the idea of sequentiality does not exist in an MLP by construction. So you will have to ensure that the idea of sequentiality is embedded into the architecture, and that is why a new architecture has to be thought of. Learn what? Maybe, but explicitly, see, I keep telling you this, right? An MLP can learn anything. The thing is, if you bias it by having these kinds of explicit regularizers, it will learn it better in whatever sense, faster convergence, better trade-off between bias and variance, and so on, right. Okay, so let us look at, now with this prelude, let us look at recurrent neural networks, RNNs. Now, see, just like we had parameter sharing across space in CNNs, in recurrent neural networks you have parameter sharing across time, or the sequential the sequence indices. Okay, so there is parameter sharing across time. So I wrote time within quotes because if you look at a natural language, right, there is no idea of time, it is just the sequentiality, there is some ordinality, some ordering, that is it, right. So what does this mean? A vanilla RNN looks like this. So we have data point x to be this way, x1, x2 up to xt. Please note that this is one single data point that we are talking about. I do not write labels deliberately for a while, because I will write the recurrent architecture first and then we will write the labels. So this is one data point that we have. So we define what is called as the hidden state ht superscript and subscript. So ht is equal to, first you do okay, so before that, before you define the hidden state, there is a pre-activation that we define. Zt is equal to w1 ht minus 1 plus w2 xt, sorry, w2, do not copy it yet, let me just complete it. Do you mind if I just switch this notation from being a superscript to a subscript? I did not do subscript because we have been using subscript to denote data points, right, but now I will be, at least for the recurrent architecture, I will use subscripts not to denote data points but to denote the temporal index. Okay, so please note this change, and otherwise I will have to write, there will be a subscript here and superscript there, it will confuse you. So this is xt plus some b1, okay, and then we define ht to be some sigma times zt, and then you make the output y to be some w3 ht plus b2. Okay. So, this is one of the definitions of RNN. So, why am I saying one of the definitions is because as we will see in the end of this class, there are multiple ways to define an RNN, but this is the fundamental idea. So, now please note this. So, what is happening here is that in a recurrent neural network, we define what is called as a hidden state HT. Now, mathematically speaking, all of these are either linear transformations of data or nonlinear composites of linear transformations of data. The hidden state is nothing but a nonlinear composition of linear transformation of data, right. So, ZT, which is similar to the pre-activation function that we were using in an MLP, it is simply you take, so there it was W transpose or W times X was the pre-activation. Now, here in a recurrent architecture, it is a function of both the input X and the previous hidden state, okay, because there is sequentiality. You will have to ensure that there is the sequentiality that is maintained here, and HT, which is the current hidden state, is a nonlinear composite of ZT, which is the current activation or pre-activation, and output is simply a linear transformation of the current hidden state. Does it make sense? Okay, so this is called, this is sometimes referred to as a single RNN cell. If you look at some of the architecture, some of the descriptions and textbook, they call this a single RNN cell. So, what's happening here? See, please note the equations, and mathematically it is pretty simple. How do you get H0? H0 is initialized randomly, okay. Now, ZT, which is the pre-activation, is taken as a linear function of the previous hidden states and the data, both scaled by some matrices, and W1, W2, W3 are what we are going to learn through ERM, right. And the current hidden state is some nonlinear composition of ZT, where sigma is some nonlinearity, some sigmoid actually, it can be hyperbolic tan or the sigmoidal function or anything, and the output is taken to be a linear transformation of data, okay. In fact, there can be a nonlinearity here as well, you know, if you are looking at classification problems, you need it to be bounded between 0 and 1, right. It is just linear and non-linear. See, what the reason I am sort of de-emphasizing on this particular structure is that, as we will see later, okay, this structure is not sacrosanct in the sense that you can actually change this, meaning as long as there is a sequentiality. The recurrence form of recurrent neural networks comes from the fact that the output and the pre-activations are functions of the previous hidden states, that is it. And these functions are linear functions, or rather non-linear composites of linear functions of either previous activations or previous hidden states and data. So, there can be multiple combinations that can be worked out for this, and that is what gives rise to different architectures. And in fact, I was going to mention this anyway, I will mention this. There is a paper, 2015 paper that came out, where the authors examine, I think, you know, a few thousands of ways of combining this and show that all of them on an average lead to a same performance, as long as there are a few properties that are met, which we will see. So, that's how you sort of distill everything out, okay. But this is one of the primitive architectures of how RNNs are written, okay. Now, if I mean, there is one diagram that people write. So, how is it done is that if this is one RNN cell, then what is happening is this. So, there is XT, and this is W2, and we have HT minus 1, and this is W1, and this is ZT, but there should be a sigma here as well, right. So, sigma will give you HT. So, HT is what goes out, and this is YT, and we have W3 here. This is one RNN cell. I mean whatever I have written using math, just written a diagram to show that. Is this okay? Just a second. So now okay, so maybe before I continue I will take questions. Yeah, tell me.
So the doubt I had was, do we run this back propagation algorithm for every single time step? Like at one time step, we then
Hold on to your question. I have not talked about how to do back propagation for this yet. Just 5 minutes. I'll get there. Yeah. Any questions on this? The way the architecture is? Not said that yet. Yeah. So I talked about parameter sharing across time. Okay. So what does that mean? So this is called, typically what happens is there's some people write it this way. Have you seen this? This sort of a diagram. Okay. So why is this? This is called a rolled RNN, right? So you have to unroll it. Just complicated terms to just say that the next RNN cell will have the same W1, W2, W3 and it continues. So this is parameter sharing across time. Across time, the weight matrices or the parameters do not change, no matter how long the sequence is. Make sense? Yeah, that's the kind of regularization that we are imposing here. There is in CNNs there was parameter sharing across space. Here there is parameter sharing across time. So this is what is called as an unrolled RNN. So it's, I mean use the same cell RNN cell multiple times at different times, or you just unroll it. You know what? Then how does it know? This is xt, this is xt plus 1 and so on, right? So how does it know what is the next data point, that is the next vector that is coming in sequence? Have you noticed what changes here? The parameters do not change. What changes? H will change, the hidden states will change. Why? Because it is a function of the current input and the previous hidden states. And now you know why it is called an RNN. By definition, the hidden states are recurrent. There is recurrence here, and I can unroll it, right? I can write ht minus 1 in terms of ht minus 2, ht minus 2 in terms of ht minus 3 and so on. There is proper recurrence here, that is why the name recurrent neural networks. You see this? Now why should we share the parameters across time? So if share the parameters across time, why should that be the case? See, it's a dynamical system, right? In a dynamical system, typically the assumption that is made is the parameters of the system does not change across time. What am I saying is that suppose we are looking at language, the language does not change across time. Sometimes it may be a naive assumption, that's why people move to something called an attention that we will see later, right? But I mean if some of you have studied signal processing, this is very similar to the linear dynamical system or a Kalman filter, where you assume the system parameters not to be changing across time. So the ABCD matrices of the dynamical system do not change across time, you keep them constant. It is assuming that the environment which you are operating in does not change across, it is not a function of time, is one reason. The other reason is that, remember we said that we need to cater for different sequence lengths. Right? If you share parameters across time, you can actually work with any sequence length because you are using the exact same parameters. All you need is one other cell to do that. Okay, and remember the description that we had given for parameter sharing in a CNN. No matter where a feature appears in the image, our neural network has to, or rather our neuron has to identify where it is. Similar explanation comes in. Let's say that there is a neuron that detects whether a given word is a noun or a verb. No matter where it appears in the sentence, it has to determine whether it is a noun or a verb. That is why you do parameter sharing across time. Make sense? Yeah. Now that comes with its own problems. There is this infamous problem of vanishing gradient that comes in, which we will talk about in a while. But yeah, so did you understand the architecture? There is parameter sharing across time. Now how do we accommodate the output random variable here? Depending upon what your architecture is, or rather what your problem is. So let us say that your problem is that of classification, then the way to do it is at the last cell of the RNN, okay, when you have X capital T, only that cell will have the output, okay, all the other cells will not have an output. I mean, meaning it will give you some output, but the loss will be computed only here. Let us call this y cap. So there is y cap and y. You compute this at only at the output. If you take the example of emotion recognition from a paragraph, then the entire paragraph is given one word at a time to the LSTM or rather RNN, right? And at the last cell, whatever it gives as an output is where you tap the outputs, and this the output of this. So basically, suppose you are solving a k-class classification problem, then this y will be softmax of W3HT, and the softmax will be of length k, so that you get a k dimensional one hot vector. Compute the output only there and then back propagate. You ignore the outputs of all these cells. Do you see what I am saying? Yeah. You don't know, you don't have to, because this is not recurrent. It is just a function of the current hidden state, you do not have to compute. Yeah. Is it clear? So this is for classification. Suppose you have to solve translation task, where input is a sequence, output is a sequence. What do you do then? Yeah. So tap the output at each of the x's, right? So the way to do it is, so give entire input. There are multiple ways to do that as well. So one way to do it is, so you have so typically this is how it is done, okay, in an auto-regressive way, where you have x1, x2 up to xt, x capital T, you do not tap, okay. Then the next cell, okay, you start tapping the output. This is y1, okay. Now take this y1 and give it as an input to the next cell and get your y2 and do that, keep doing this. So this is the famous encoder decoder architecture of generation, where you have the input sentence or input sequence, compress it completely. So basically what you are saying is, you are trying to compress all the information about the input sequence in the the last hidden state of the input cell, and you give that as an input to the next set of RNNs or next set of cells and ask it to give the output. Is it okay? These are, as I said, no, these are Lego blocks. You can just plug and play them the way you want, depending upon what problem are you solving. One second, I will take questions in a while. Okay. Now there can be two questions which I will answer right now. Now when do you stop this? You take y1 and give it as an input to the next one, okay, you get y2 and take, when do you stop? In your data, when you are annotating your data, you also have a particular word, okay, which you call as the end of sequence word, EOS, okay. Wait till your RNN outputs an EOS, stop then. You get it? So every sequence, the data itself, the input data itself will be input sequence in one language, then EOS, output sequence corresponding to that language, then EOS. So you have an input sequence, output sequence with EOS. Now when you solve it using the same ERM with supervised learning. During inference, okay. By the way, have I told you what inference is so far? Okay, you have a model, right? You do ERM, have a model, and then you pass your test data to your model and get the labels on that. No, that's called inference. Testing basically, right? Testing is also referred to as inference in ML, okay. I thought I had mentioned that somewhere sometime in the course. Anyway, so during inference what you do is that give the input sequence, okay, tap all the hidden states, and then take the hidden state and after the end of sequence in the input sequence comes in. So whatever the RNN gives you as input is your output, because that is, you have trained your neural network in a way where everything that starts after the first EOS is your output, okay. And the next, whenever the next EOS comes in, you take everything between two EOSs as your output, that is it, and whatever comes in between is your target translated rather output sequences, that is it. Still not told you how to do backpropagation here. Well, I'll come to that in a while, but I'm just talking about how to design, make architectural designs while solving these kinds of problems. Okay, questions now? You had one? Yeah. Go on. Yeah.
Why is a function of just HT rate?
H capital T. Yes.
We are not giving X as input.
That's precisely why attention came. We'll come to that in a while. Yeah. So right now the way this architecture is written, the output is only a function of HT. So you are assuming that everything about the input sequence is compressed in H capital T. Number of RNN cells depends upon, okay, the question is how do you know how many RNN cells are there? It depends upon the number of sequential time steps in the input, and that's a variable. Every input will have different number of RNN cells in each data point, exactly. That's why you have parameter sharing across time. That's why it's not an issue. All you need to do is just repeat that same cell and do these operations again. And by the way, I have not told you one other thing. See, this is only a single layer of an RNN. I can actually stack multiple of these across depth. You see that? So, I mean, this need not be Y. So, I can have another RNN cell, I can have another RNN cell and so on. I can do it depth wise as well. You understand? So, when you build an architecture, an RNN architecture, you need to specify what's the depth of this RNN architecture, and that's how many hidden layers you will have across depths. Okay? Yeah.
Like you showed the corresponding MLP for the CNN, can you also show the corresponding MLP for the
Good question. So, how should I look at RNN as a modified MLP? Can somebody take a guess? I thought I would ask this question in the exam. Think about it. Yeah, I will not answer it right away. Think about it. You know, how do you modify an MLP so that it turns into an RNN? Okay. Anything else?
We are not even calculating the HT plus 1 on the decoder.
Why not?
Could you write equations from the decoder?
Same thing, right? So that would be a function of H capital T. That's it.
T plus 1 we are not calculating.
It is here. Yeah.
Could you write the equation for the decoder?
Exact same equations. Exact same equations. Yeah. But the hidden state corresponding to the input is compressed in one hidden state, and then it is carried forward. That's it. Okay. Okay. Let's move on. See, as I said, suppose you are let's say. Okay, so this way, this also is a sort of generative model, that conditional generation. That's why I told you in the beginning that. Okay, here is a statement that I am making. See, even a classifier is a generative model. I generally make this statement in the very first class of my next course on generative models. But yeah, so I'll tell you why. What is a generative model? It's a sampler. Okay, it's basically a sampler from a distribution. Now, a classifier is a sampler for this conditional distribution, isn't it? Isn't a classifier a sampler from P of y given x? The output of the neural network will give you a distribution on P of y given x. It's a sampler. Okay. Now, any sampler is a generative model. So, a classifier is also a conditional generative model in this sense, that conditioning on an input random variable x, okay, you are sampling from another random variable y. So, P of y given x is what you are sampling from. Now, that is why a machine translation model, right, which is an RNN, can also be seen as a generative model, because conditioned on x, you are sampling from P of y given x, where both x and y are sequences. You see what I am saying? See, that is why I do not want to make this distinction that, oh, there is a generative model and there is a discriminative model. Both are samplers. Okay, what distribution are you sampling from in the question? Typically, in the community, if you sample from P of x given y, then they are called generative models. Now, if you look at all the the modern day LLMs, okay, they are actually sampling from P of y given x, where x is your input prompt. You see that? Okay, and I mean I do not know if you noticed this, right? I gave y1 as an input while generating the next sequence, right? This is called auto regressive generation. So what I am doing is I am modeling P of y given x, okay, as a product of P of yt given, this is how I am modeling implicitly. By doing this, all I am doing is I am modeling P of y given x. Of course there is a conditioning here, everything is conditioned on x. This is the typical autoregressive model, right, where the tth dimension of data is modeled, the conditional distribution of the tth dimension of data is conditioned, is modeled as the product of the previous conditional distributions. That is the autoregressive modeling. Anyway, so I will talk about autoregressive modeling later in detail, so this is just a passing remark. But anyway, so now you see why this is a generative model, in the sense that it's any sampler is a generative model, and this we are here sampling from P of y given x. Okay. And yeah, so the point that I wanted to make was, let's say that you are solving the problem of image description, as I said. The way to do it is start from an image, okay. So have CNNs and take a vector, and this vector is given as an input to an RNN. You generate the description. You see that an image goes as an input to a CNN, and you take a you have an MLP in between, you flatten the layers, take a vector and give that vector as an input to the RNN, and then train it in an autoregressive manner or have an autoregressive architecture, so it generates one word at a time. Okay, that is how it is. So the kind of data that you need for that is you need an image and the corresponding description for it. Okay, any questions so far?
The RNN cell for the decoder structure will have a different architecture, right? Because we are giving y1 as input to the next cell, so some other weight will also be.
No, there is no weight there. You just give it as an input to the next one. That's it. See, I can actually take this off. Oh, sorry. Take this off and write the input to the next cell as y1. The same thing. All I am saying is there is no explicit input to the decoder cell. You just take y1 and give it as an input to the next cell. That's it. We will stop here and continue in the next lecture.